Hey guys, welcome to the Penrith sheet. In this part of the video I'm going to show you my method for drawing a cross-section for these uniformly dipping rocks and to see what they look like in the subsurface. This is your Penrith map, and you can see that most of the outcrops in this western half of the map, they form these strip-like exposures that run down the length of the map. Okay, that sort of exposure pattern indicates that these rocks have a uniform dip. We don't see any repetition, so we don't think that they're folded. In this part of the map we don't see any sort of bullseye-like exposure patterns that are parallel to the ground contour, so we don't think that they're horizontal. And the outcrop patterns themselves, they're not perfectly linear and straight across the region. They kind of bend and deflect around the topography, indicating that they're not perfectly vertical. They've got some angle of dip. So that's the sort of story in this region of the map, where we go from the Carboniferous limestones to the Carboniferous millstone grit and the coal measures, before there's an unconformity between these Carboniferous rocks and our Permian sandstones. So that's the general stratigraphy. But then as we get to this point, you can see that our Permian sandstones and Triassic sandstones, they've been truncated by this rather significant set of faults. Down here you can see the name, the Lanthwaite fault, and here's the Elsk-Gill fault, and you can see that that's truncated these Permian sandstones, and to the eastern half of the fault has emplaced next to them some of these Carboniferous limestones, these blues and oranges. Now you can estimate the amount of displacement along that fault by looking at the stratigraphic thickness that's been lost between our Permian sandstones and our Carboniferous limestones. When I say lost, I mean the juxtaposition has brought these very much older Carboniferous rocks up to in contact with our much younger Permian rocks. Okay, so looking at your stratigraphic column, between those 2 points you've lost the entirety of the millstone grit series as well as the coal measures. Now when you look at the rocks on the eastern side of the fault, you can see that their outcrop changes completely relative to those on the western side of the fault. On the eastern side of the fault you can see that these outcrop patterns are forming these concentric rings which are parallel to the ground contours in most places. And that indicates that the rocks on this side of the fault, on the eastern side of the fault rather, are still pretty much horizontal. They're not dipping like the rocks on the western side. The rocks on the eastern side, they look like they're relatively flat. Now this fault isn't the focus of our cross-section today. Indeed, our cross-section doesn't quite extend that far, but I just want you to see this difference in outcrop styles between rocks which have a dip, a uniform dip, and rocks which are still largely horizontal. So just take a moment to look at that difference in outcrop pattern. Now what we're going to do is start drawing a cross section, and what I've done is used 2 bits of tape to show the 2 corners, the 2 extremes of our cross section. So what we're going to do is draw a cross section along that line to show what the subsurface geology in the area would be doing. So what I'm going to do now is zoom in on that area, and then we can get drawing. I've got my tools ready. I've got my propelling pencil, I've got my compass, my protractor rather, I've got my ruler, I've got a delightful range of colouring pencils, I've got a calculator, and I've got a pen to write myself some little notes as we go along. So if you want to get together your tools and then we can start drawing our cross section, and then that'll help us finish up with our lab. Okay, see you in a second. Okay then guys, so now this part of the video refers to question number 5, which asks you to construct a sketch cross-section, and that's one without topography, between the points 470, 400 and 540, 450. So what I've already done is gone to the 470 grid line and the 400 grid line, and that's this piece of tape there. So that's my first point on the cross section. And then the second point on the cross section, 540, 450. So what we're trying to do is see the subsurface geology along a line that connects these 2 points. Okay, now with any map that you have, never ever mark it. I'm just doing it so I don't have to keep knocking the camera as I clumsily move my piece of paper around. Okay, so this question asks you because the dip of the rocks around here isn't particularly large, they're only dipping at about 10 degrees or so. This question has asked you to construct a cross section which has 4 times vertical exaggeration. So we're going to stretch our rocks and change our angles of dip. In order to do this, we'll need to draw the dip of the beds to take into account this exaggeration using the formula that's given to you at the bottom of your screen and on the PDF of the lab book. But let's get to that in a minute, and first let's start drawing our cross section. So I've got my strip of paper, and I've lined up my strip of paper so that it goes through the corners. This is B, and this intersection here is A. And I don't have to draw a hill profile because we're doing a sketch cross section. So instead, what I'm going to do is straight away move on to plotting my geological contacts. So from A all the way to this point, we're in the Carboniferous Millstone Grit. So I'll just give that an MG. And then we've got a thin sliver here of the coal measures. And then all the way from there until there, we're in this Penrith sandstone. And then we've got a fairly interesting interbedded sequence here in the Permian Eden shales, and I'm just going to mark these thin beds, these dolomite beds that are in the Permian shales, and mark on in between them as and then once we're outside of the Permian shales, we've got this thin dolerite dike, which either side of it we're into our Triassic St. Bees sandstones. Now also, what we've neglected to put on this cross-section line are we have these faults which I'm marking in a different pen so I can tell them apart from stratigraphic contacts. I've got one there, and I've got this other one, the scratch mill scar fault there. And right now I can't see any other contact that I should plot onto my cross-section line. I think that's all of them. So let's move it away, and if you're like me, you tend to learn things better if they've got some sort of colour to them. So what I'm going to do is just mark on my cross-section line. I'm going to mark on the colour of those rocks. Slightly difficult when you've just got some shades of grey, but I've got my millstone grits which are a slightly lighter grey than my coal measures. And then I've got an enormous expanse of my Penrith sandstone in orange. Yeah, all the way up to there. Then I go alternating yellows in my Eden shales with these purple dolomites embedded, and then I'm into my St. Bees sandstones, sort of almost the right colour. And then let's use a hearty red for my dolerite dike. Okay, so let's move that section off the line, and then let's have a little look around to see if I can get some quantitative data about the dip of the bed. And I don't want to stray too far away from my section. There's no point looking way over there or way over there for the dips of the beds, because some of these rocks, they might kind of flex, their dip might change. I want to draw the dip of the rocks as close to my thin section line as I possibly can. So I'm just having a little look around, and just I think off to the side of the camera here I can see dips of about ranging somewhere between 12, 15, 5 degrees over in the St. Bees sandstone just to the west. And then if we went this way, just on this side of the cross section, we can see that there's a couple of 10-degree dips in the Carboniferous rocks. So what I'm going to do with my faith as a geologist, I'm going to assume that if our rocks are dipping somewhere around between 5 and 15 degrees on the east side and about 10 degrees on the west side, I'm going to assume, because I don't have any more specific information, that all of these rocks are dipping at about 10 degrees over onto the east. Okay, so those are my sedimentary rocks. That's the dip of my sediments. Okay? Now, looking at the faults then, they don't typically have any dip associated with them. Instead, you'll have to infer what the dip is based on the outcrop pattern of the fault itself. And our cross section has crossed these two faults, the Scratch Mill Scar fault and the Abbott Muss fault going this way. They're the only two that cross our cross section line. Now I'm looking at the Scratch Mill Scar fault, and I think for the region that our cross section goes through, this Scratch Mill Scar fault is very, very linear. It's almost perfectly straight. So I'm going to assume, without having any better information, that this Scratch Mill Scar fault is vertical. For the same reason, looking at the Abbott Muss fault over that entire length, that too is straight. It's got a little bit of a wiggle up in the northwest there, but I'm going to assume again, without any better information, that this Abbott Muss fault is also vertical. So that's almost everything except for our dolerite. And again, we don't have any dips on our dolerite, but if we follow this dolerite dike, this thin little red unit that cuts across the entirety of the stratigraphy, cuts across the faults, I'm going to assume that based on the linear nature of that outcrop, that the dike also is vertical. Okay, so that's all of my information that I can glean from the map. I just want to check, comparing my map to the geological column, the stratigraphic column on the left hand side, all of the contacts, let's see, between the millstone grit and the coal measures. Oh, that's interesting. we have between the millstone grit and the coal measures, we have a little unconformity there, a gap in geological time. And between our millstone grit and our Penrith sandstone, there's another unconformity, and between the coal measures and the Penrith sandstone, there's another unconformity. Okay, it's a special kind of unconformity, I guess. This is probably a para conformity, where there's a gap in geological time, but there isn't an angular difference between the dip of the beds. They're all still dipping in the same way. There's just gaps in between them. But then within the Permian rocks and the Triassic rocks, the Penrith sandstone and the St. Bees sandstone with the Eden shales, they're all conformable. Okay, so at this point, if you had a cross-section panel which looked like this, you've got all of the information that you need to start drawing your cross-section. Okay, so now we're onto our cross-section panel, and we can take the data from our cross-section that we made using the map, and we can plot it onto our cross-section panel. So here's our cross-section strip that we made with all of our data, and what we're going to do is use this data to show what the cross-section would look like and what the geology would look like in the subsurface. Now, irritatingly, and this always happens when you turn an image into a PDF, you can see that my A and B on the map is not quite the same size as the A and B on the cross-section. I mean, I'll do that better at some point, but you know, life is definitely far too short. So now what I do is line up A and B as close as I can. I'll just put in a new A and a new B just to work on this at the moment. And then I'm going to go along onto the top of my cross-sectional panel and mark on the contacts. Yep, and then with the fault, I'll just mark that on lightly as a fault, and then these stratigraphic contacts, which are unconformities, just as a little note to myself. I'm going to remember that. And it's always good to have one of these pencils that has a rubber on the end, so that you can remove these little notes to yourself later on. Okay, I'm not going to bother putting the colour in, or shall I? tell you what, I will. I'll just put on a little kind of very, very thin veneer of colour, just to make it feel like I'm making progress, which, you know, funny enough, we are. So from there to there, we're all in orange, we're all in the Penrith sandstone, big, thick bed of it. Just a very thin veneer on the surface, and then we're into our Permian rocks that go from there all the way to there, with these little beds of dolomite in between them. And then what we've got our Triassic St. Bees sandstone, which goes like this, and then there's that very skinny dike, that dolerite dike that's just there. Okay, now what I have to do is figure out just which one of these features I'm going to plot first. And if we skip back to the map a second, if I just lift this up so we can see the map, we have to figure out what the youngest feature is. And this map is fantastic. It's got some great cross-cutting relationships. we can see that we've got this sequence of sedimentary rocks that goes from oldest to youngest. And we can see that that entire stratigraphy has been cut by this dolerite dike. You know, these sediments must have been there before the dike could have come and cut them. Now this dike, there isn't a cross-cutting relationship. Oh wait a minute, look, there is. If you follow the Scratch Mill Scar fault just to the northwest, if you continue up just off the view of the camera, you can see that that fault has displaced this dolerite dike. So the Scratch Mill Scar fault must be the youngest thing. Then the next youngest thing must be the dolerite dike. And then the next youngest set of rocks are our Triassic, then Permian, then Carboniferous. Okay, so that's the order in which we're going to draw them. We're going to draw our faults first, these northwest, southeast trending faults, the Scratch Mill Scar fault and the Abbott Moss fault. Then we're going to draw this skinny little dolerite dike. And then we're going to draw our sedimentary rocks. Okay, so that's the order in which we'll draw our things, and we do it that way so we save ourselves any extra rubbing out. Okay, so next thing that I need to get out of my toolbox is my protractor. And then let's start drawing some angles for the order in which we're going to draw our youngest things first. We've already established that the youngest things based on cross-cutting relationships are the faults. So what I'm going to do is get my protractor, crosshair, and then drop that onto the top of the cross-section panel at the point at which I've got my Scratch Mill Scar fault. Then what I'm going to do using my propelling pencil is draw that angle of dip to 90 degrees, because I'm going to assume this is largely a vertical feature. Okay, then what I'm going to do to show that fault in the subsurface is just draw those 2 points where it crops out on the surface at the right angle, and hey presto, I've got a vertical line. It's probably the most long-winded way you've ever been shown to draw a vertical line in your life, but this is just so you get into the process. Next fault is the Abbott Moss fault, which I'm also interpreting to be a vertical feature. So I get my crosshair of the protractor onto the point at which it hits the cross section on the surface, and I mark on at 90 degrees, and then I connect those two up. And I've got my two faults. Now the next youngest thing that we had was our vertical dike, which crops out over here, and then I'm just going to draw these two contacts of it, one there and one there, and so I've got my vertical dike. Okay, then what I can start doing is drawing in our stratigraphic contacts. Now I've assumed that all of these guys, or I've not assumed, I've interpreted from the relatively consistent dips across the area that all of this package of sedimentary rocks are dipping at about 10 degrees towards the east. That's what the dip arrows are telling me. But if you remember to the question, we're going to have to draw this cross-section with some vertical exaggeration. So what we're going to have to do is modify these dips to take into account that vertical exaggeration factor. Okay, the equation is given to you in the lab, but the equation, if I were to write it out here, is the exaggerated dip is equal to the inverse tangent of the actual dip, or the true dip, multiplied by the exaggeration factor. Okay, so substituting in what we actually have, so that's the that should be the tan of the true dip. So it's the inverse tan of 10 multiplied by our exaggeration factor, which I think in our lab is, let me just double check that, is 4. So our vertical exaggeration factor is 4. So using my calculator, tan of 10 multiplied by 4, taking the inverse tan of that answer, tells me that the dip of our rocks that we're going to be drawing, our exaggerated dip, is actually 35 degrees. Okay? So because we've stretched this cross-section so we can actually see the dip of the rocks instead of just being a bunch of parallel lines at 10 degrees, we're going to give them a nice meaty dip of 35 degrees. Okay, you can't just multiply the dip by 4 to get an exaggeration factor. There's actually some level of maths behind it, but that's the formula that you need. Take the inverse tan of the true dip multiplied by the exaggeration factor, and that'll give you the exaggerated dip that you're going to draw. Okay, so these 10 degrees then become 35 degrees. And that's what I'm going to start drawing my contacts as. So, let's keep going with the next youngest things, which are our Triassic and Permian sandstones. And what I'm going to do is, for each one of my stratigraphic contacts, I'm going to line up the crosshair of the protractor with the mark on the top of the cross section, and then I'm going to count round horizontal 0, 10, 20, 35. And then continue that contact up until the dike. Now when it hits the dike, it's not going to just pass straight through the dike, the dike is in the way, but because when dikes are in place, they're not really associated with much slip. They won't displace contacts, they'll just kind of pop open the crust, intrude, and then go on their merry way. So what I'm able to do is continue that contact on the other side of the dike, okay, which shows how the contact between our Triassic St. Bees sandstone and the Eden shales, how that will continue past the dike. Okay, then what I'm going to do is continue that process. Got another one at 35 there. If I continue that and then step over the dike, and then I'll put its bottom contact. And when your lines are this close together, you don't have to keep marking 35 degrees on. It'll probably introduce more error than otherwise. You can just trust yourself to draw parallel lines. And then that's pretty much this part of the section solved. Now if we wanted to feel better, we could colour that in, but right now I'm just gonna crack on. And then I haven't got any stratigraphic contacts within this Penrith sandstone. And so what I'm going to do is, using the relative thicknesses of the Eden shales and the Triassic rocks, I think from the thickness that you can see on the stratigraphic column, I think that the thickness of those rocks is similar to the thickness of the Penrith sandstone. So what I'm going to do is say from about here at 35 degrees, that would be my interpreted base of the Penrith sandstone. Okay, so I'm just continuing. So just draw this contact and then continue it down past the other side of the dike. Okay, at this point I'm going to leave this middle section, the fault bounded section of the Penrith sandstone, and instead I'm going to concentrate on the left hand side of our cross-section panel. And like I said from the start, we've been assuming that these rocks, or we've interpreted that these rocks are going to have a constant dip, which with our vertical exaggeration is 35 degrees. So I've got the base of the Penrith sandstone here and its contact with the coal measures. I've lined up the point on the surface of the cross section, projected it to 35 degrees, and I'll just join them up, but I'll stop when I hit that fault surface, because at the moment I'm not certain how much slip has occurred along that fault, so I don't really know where it's going to continue. So I'll do the same thing for the base of the coal measures. Get that in at 35 degrees and we're golden. Now, what we're going to have to do is figure out where the boundaries for the coal measures and the millstone grit are beneath this middle section of the Penrith sandstone. Now what we should do is first of all look at the map and see if it can give us any information about which side of the fault has been moved down relative to the other. So if we just go and have ourselves a little look at that scratch mill scar fault on the map. If we look along that map, the fault trace, every now and again you should see a little tick on one side of the fault plane. Now, have a look at what that tick means in the key for the geological map. And you should see that that tick denotes which side of the fault has gone down relative to the other, which side has been thrown down relative to the other side. Okay, looking at our scratch mill scar fault, we can see that the tick points to the western side of the fault, and that indicates that the west side of the fault has gone downwards while the east side has gone relatively upwards. We've had a sort of that kind of movement. So what we can do is take that information and go back to our cross section, and we can add in that sense of movement along the fault. So the way that we do that is to use a little half arrow to show that the western side of the fault has gone down relative to the eastern side of the fault. And that means that if this side, if the left hand side as we look at it has gone down and the right hand side has gone up, then we can constrain where these contacts between the Penrith sandstone and the millstone grit and the millstone grit and the coal measures, the Penrith sandstone and the coal measures and the coal measures and the millstone grit, we can constrain those to exist somewhere between here and here. There can't be any, this side of the fault, the right hand side of the fault, can't have been pushed up that much further, because if it had, then they would those cold measures would intersect our cross section somewhere in here. So we can constrain them to being somewhere within this. And because I have no other information to figure out the exact precise displacement of the fault, I'm going to say that the Penrith sandstone and coal measure contact, the base of the Penrith sandstone is there. Then what I'm going to do is get my protractor, line it up on that point at which I've just marked on the fault plane, and then drop that contact, that dip, to 35 degrees. Now, because I've interpreted this, I'm going to denote it with a dashed line. And if this dashed line represents the base of the Penrith sandstone in contact with the top of the coal measures, then I need another one to show the contact between the coal measures and the underlying millstone grit. So that's where I'm going to interpret that it would hit the fault plane. And then I plot a point at 35 degrees to that, and then I dash that in. I can also give the contact between the coal measures and the underlying millstone grit on this side of the fault by assuming, or by just using, that apparent thickness that I've assumed everywhere else. So that's about there. Get that to 35 degrees. And then plot it as a dashed line to show my relative uncertainty. Okay, we're almost there. The only thing that's missing for this subterranean geology is the stuff that's beneath the millstone grit. Now, if you look at your stratigraphic column, you'll see that beneath the millstone grit, conformably beneath that millstone grit, are some carboniferous limestones. And exactly the same way as we did over here to estimate where the base of the Penrith sandstone would be beneath our Permian rocks, where the base of the Penrith sandstone would be, we can also use the stratigraphic column to calculate or otherwise infer where the base of the millstone grit series would be. Now, based on the relative thicknesses in the stratigraphic column, I'm going to say that about there would be a good estimate. And because those limestone rocks are conformable with the overlying millstone grit, I'm going to plot that again at 35 degrees. So here we go. I've inferred that contact between the carboniferous millstone grit series and the carboniferous limestones. Now you can do that more precisely by using a calculator to look at the exact or to calculate the thickness elsewhere. But right now I'm going to use that as a pretty good estimate. So now what I can actually start doing is, now that I've finished all of my contacts, I can start colouring in my geological cross-section and get the finished article out of the way. So I'm going to start with colouring in our happy little dolerite dike in red. Then I'm going to move on to our Triassic sandstones. Then I'm going to use a yellow for the Eden shales. And my purple for the interbeds of dolomite. And then I've got this faulted area of our Penrith sandstone that on the map is orange, and that's where it's going to be on my cross section. Obviously, if you've got the time and you take pride in your work, which you all do, I'm sure, you take time to shade this correctly. But because you guys probably don't want to watch me colouring in for 10 whole minutes, I'm just going to try and do these as quickly as possible. So these dark greys are the Carboniferous coal measures. Maybe on the video I might try and edit this to speed up. Or I guess you guys could just skip over until I'm doing something a bit different. So that's our coal measures, and then very lightly, let me just show the millstone grip. Now, one thing that my cross section requires in order for it to be correct, we'll get to that in a minute. Let me just put in my general blues for my limestones. Now, one thing that my assumptions in my cross section require to be correct is that this second fault, this Abbott Moss fault, it has a similar downthrown side. So you remember the scratch mill scar fault, this one. We've interpreted from the map that, or the map is telling us that the left hand side of the fault has gone down relative to the right hand side. In order for our cross section, or my interpretation of our cross section to work, this Abbott's Moss fault must also have that same displacement. The left hand side of the fault must have gone down relative to the right hand side. So I'm seriously, absolutely hoping that when I look back at the map to double check my interpretation is correct, I'm sincerely hoping that the dip tick, or the downthrown tick rather, of the fault plane is pointing towards the west. So let's have a little look. So here's our Abbott Moss fault, which you can follow like this. And thank the maker, you can see here we've got a tick that's pointing towards the west side of the fault. There's one there, there's another one there, thank goodness, and another one there. So, whew, our cross-section interpretation holds true with our map interpretation. So we can just put those arrows, those half arrows, to show the sense of movement along that fault. Okay, that's a pretty good section so far, and then maybe just for practice what we could do is, I don't need those unconformity there, I know what I'm doing now. Maybe what I could do is just project sensibly, you know, you don't want to go to the moon or anything, the continuation of the geology above the surface. Just to show what the geology would be doing prior to modern erosional processes. So I'm just going to use the base and the top of the Permian rocks, because otherwise I'd be there for all day. And then just finish off our dike chap. And then that shows us what the geology would have done prior to modern erosional processes to give us the current weathering surface. Okay, now we're on to the point at which we need to do our housekeeping measures to give it a scale and to give it a key and so on. And because we've used this vertical exaggeration, we have two different scales. We've got the horizontal scale and then we've got the vertical scale, and the two aren't the same because we've pulled our cross section in the vertical axis to give us that exaggeration factor. Let's start with the horizontal scale though, because that's dead easy. If you think about what we've done for our cross section, all we did was take the information from the map, put it on a piece of paper, and then transfer that onto a cross section. So we haven't changed the scale of the map, we've just transferred data from one to the other. So we can use exactly the same scale for our horizontal scale on the cross section as is provided to us by the map. So if you look at the base of your map, you should see a scale, which is 1 to 50,000. And because we haven't done anything to our horizontal dimension, we've just taken information from the map and put it on the cross section, we can use the same scale. Now, because we've exaggerated our vertical scale, we've stretched it by 4 times. For every unit, we're seeing 4 times less than compared to the horizontal scale, if that makes sense. We've stretched we started with a horizontal scale and then we stretched it by a factor of 4. So our vertical scale is simply 50,000 divided by 4, which comes to 1 to 12500. Okay, that's pretty good. Then the only other stuff that we need are to put our rock types on, and I think we've got 1, 2, 3, 4, 5, 6, 7. So on the left hand side here, I'm just going to give me a key of 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'll just turn those into squares. You guys can obviously do this with a ruler, and you can hold your ruler straight, I hope. And then we simply add in usually in stratigraphic order that makes the most sense are rocks. So what I've got is at the base I've got my carboniferous limestone, then I've got my millstone grit, then I've got my coal measures, which then give way to the Penrith sandstone. Then I've got my Eden shales with intervening or interbedded dolomites, and then on top of those I've got my Triassic St. Bees sandstones, and then separate from that I've got my dolerite, so we could give that we could give those names. then coal measures, and then let's go for the millstone, and then we've got carb limestones. Okay, at that point, you know, you're pretty much done. Maybe you could say which fault they are. So this is our Abbott Moss fault, and this is our Scratch Mill Scar fault. And then at this point, presentation issues aside, you've got a defensible cross section for the area. So have a go at this yourself, and we'll get together when things are back to normal, and we can see how well we've done in understanding generation of cross section. Thanks for listening, guys. I'll see you in the next video.